Так, ну что, все вроде бы пошло. Теперь давайте, можно начинать.
Одну секунду, я закончу файл пересылать со слайдами. У меня просто технические сложности. Да? Вроде как. Сейчас они разрешились. Так. Ну все, я вроде послал слайды Паши Гавриленко. Мне сказали, что доклад делать надо на английском.
That's right. Let's go.
Okay, so let me share my slides. Okay. So thank you very much for the opportunity to give this talk. Today I'll be talking about conformal blocks in conformal field theories in 3 dimensions and higher dimensions. So this talk is going to be, I guess, mostly a review talk, but also hopefully I'll have time to discuss some of the recent results from this paper, which we published last year with Reggie Ferramili and Luca Iliesha. And I should say that I don't know the audience very well here, and I tried to make the slides not very technical and try to include kind of various points of view in conformal blocks. But since I didn't include very much technical material in the slides, it would be great if you would ask me questions when, like in situations when you're interested to hear maybe more about some particular point and so on, so that we can have a more productive seminar. So let me start with some motivation, and I cannot really give justice to motivating why study conformal blocks in one slide, but I'll just to say a couple of words. Conformal blocks are kind of very important objects in conformal field theory, and there are many reasons to care about conformal field theories, and most popular reasons, and as far as I know, are the fact that conformal field theories describe fixed points of RG flows. That could be infrared fixed points, ultraviolet fixed points, and this kind of point of view includes various statements such as that the conformal field theories describe long distance physics at continuous phase transitions at critical points, that let's say they describe the lower energy limited of gauge theories in conformal windows and so on. Another popular reasons to care about EDA-CFT, about CFTs is that EDA-CFT correspondence, which says that, of course, quantum gravity in ADS is to some or other degree is equivalent to conformal field theory in the boundary, and therefore let's study conformal field theories because that will help us understand quantum gravity. And finally, we might care about conformal field theories just because there are some quantum field theories with rich set of symmetries which have some interesting mathematical structure, and it's just interesting to study such objects. Now, as I said, the conformal blocks are kind of central to CFTs in the sense that we'll introduce them in a bit later, and they kind of compute lots of things, and there are many ways they are used in study of conformal field theories, but say for the purposes of this talk, I'll just focus on one particular application, which is that recently there was a lot of progress on understanding conformal field theories numerically by analyzing crossing equations, and I believe Slava Ryczkov recently gave a talk here about this. So I'm not going to go into details of that, but the kind of the main results in the field are that people can constrain critical exponents, anomalous dimensions, OP coefficients of lots of operators and various strongly interacting CFTs like 3D Ising, CFT, and so on. And there is a ton of results, but all these results come from analyzing crossing equations, and crossing equations are equations which involve conformal blocks. So to do any of that, we need to be able to compute conformal blocks. And as I said, conformal blocks are also important for other things, but just for the purpose of this talk, let's just focus on this motivation. So this is just to say a couple of words, and I'll now go into more detail on what the conformal blocks are. And first, let me kind of specialize what I will mean by conformal field theory for this talk. It's going to be, a conformal field theory is going to be given by a set of local operators, which I'll write as OI of x, where x is some point in Euclidean two-dimensional space. And for these operators, we specify a set of correlation functions, which are just kind of expressions of this form, where we insert operators various positions, and these correlation functions related in some particular configuration are just some complex numbers in general. And we want these correlation functions to be conformally invariant and satisfy a convergent to P expansion, which is to say that when we take a pair of operators inside of this correlation function, we can replace it by an infinite sum of all other local operators with some coefficients. And if we had the original operators points x1 and x2, and the operators we replace them by are at x3, then this expansion should converge whenever x1 and x2 are the only operators inside some sphere of drawing around x3. And we'll get a bit more into the detail of that later. But this is kind of what will be meant by a conformal field theory for this talk. And of course, this OP is known in 2 dimensions as well. This OP can be applied in various ways to these correlation functions, and all these ways should be consistent because there is just a single correlation function. So an important player in all the story is the conformal invariance. So let's just review briefly what the conformal invariance is in higher dimensions. And conformal maps are, of course, just some maps which don't necessarily preserve the metric, but allow the metric to be rescaled by some coordinate-dependent scalar factor. And as usual, we can study this kind of what conformal maps there exist by studying infinitesimal conformal transformations. And so we look at some vector fields which generate these transformations, and the condition that these transformations preserve the metric up to a factor lead to this equation on the on this vector fields in flat space, and such vector fields are called the conformal Killing vector fields. Now, this equation on the left side just contains kind of the variation of the metric under the infinitesimal transformation, and what we're saying is that the variation of the metric should be proportional to the metric itself. And here I'm just working in flat space with some proportionality coefficient, and we can remove this proportionality coefficient by subtracting the trace, so that we get an equation which is just in terms of epsilon. And famously in 2 dimensions, this equation has infinitely many solutions, but in higher dimensions, there are undefined many solutions to this equation. And this is not very surprising because you can count the number of equations, you can count the number of functions in higher dimensions, higher than 2 dimensions, there are just more equations than there are functions. And so it's maybe more surprising that there are any solutions at all, but anyway, we can study this equation. We can find all the solutions, and we find the following vector fields. We get the vector fields which generate translations, the vector fields mu. We get vector fields that generate dilatations, vector fields generate rotations, and some special conformal Killing vector fields which give kind of the non-trivial conformal transformations which exist in higher dimensions. Now, so we get this vector fields, and we can ask what is their algebra, and so we can go ahead and compute the commutators, and we get some particular expressions for the commutators. And here I generalize to a matrix H, which is still flat, but can have an arbitrary signature, not necessarily delta. And since this is some concrete Lie algebra with some real structure constants, we can try to identify what this Lie algebra is, and depending on the signature of this metric, we get to choices. If we choose Euclidean signature, then the algebra that we get is SOD plus 1, 1, which we sometimes call Euclidean conformal algebra. And if we use the Lorentz metric, then we get the algebra SOD, 2, which is sometimes called the Lorentzian conformal algebra. And so conformal field theories are conformal field theories which are invariant under such conformal transformations. And we know that in quantum field theory, when we have a set of symmetries, the symmetries are represented by unitary or anti-unitary operators in the Hilbert space. Now, the anti-unitarity is important for like time reflections and so on. So in our case, we'll just have unitary operators. However, when we talk about symmetries, it's important that for space-time symmetries, which depend on the signature of the space-time, it's important that we take the symmetries in Lorentzian signature. And it's easy to see that for Euclidean signature, the space-time symmetries are not represented by unitary operators, because, for example, the standard Euclidean time translation is given by e to the minus ht, which is certainly not a unitary operator. And so, if you want to get unitary operators, we should use the Lorentzian signature symmetries, and these form the SOD, 2 algebra. So I always use the convention in which all my generators are anti-Hermitian. So often in physics we write that the generators are Hermitian, and we write the unitaries as e to the power I times something. Since in order not to have this i's floating around, I'll just always use anti-Hermitian generators. E for translations, K for special conformal transformations, D for dilatations, M for Lorentz transformations. So this anti-Hermitian operators satisfy the algebra, which is just comes from the algebra of vector fields, and this algebra is SOD, 2. And it is the SOD, 2, which is unitary acting on Hilbert space and not SOD plus 1, 1. Now, in 2 dimensions, we have the algebra of vector fields is the Witt algebra, and the algebra that acts in Hilbert space is the Versor algebra, which is a central extension of Witt algebra. And here in higher dimensions, since SOD, 2 is semi-simple, we actually don't have any non-trivial central extensions, and so this is directly the algebra that we have. And there is no central charge that enters the symmetries. Okay, so now that we have some conformal generators, we can ask how they play with local operators. And an important notion is the notion of local primary operator. And we call a local operator a primary if, when inserted at the origin at x equals 0, it commutes with special conformal transformations, and it transforms in natural way under dilatations and Lorentz transformations. Under dilatations, it just transforms to some eigenvalue, which we call the scaling dimension. So delta is just some number. And under Lorentz group, it transforms in some finite dimensional irreducible representation of the Lorentz group. So A is, B and A here are the spin indices of this operator. So for example, for scalar operators, this transformation will be trivial. This matrix will be 0. But for something more non-trivial, like traceless symmetric tensors, there will be some non-trivial matrices L here. And Given these properties, since an operator at a arbitrary point can be obtained by just applying the translation generator and we know the algebra, we can get the commutation relations of O of x with all conformal generators for any x. But these are kind of cumbersome and we won't really need them. The important point is that by working through this, you can check that for primary operator, the statement for finite conformal transformations, so not infinitesimal, but finite conformal transformations given by some unitary operator u, which sends x prime, is just a statement that acting on a local operator, the local operator gets sent to some new point. So if x was sent to x prime, the local operator is now at x prime, and it just gets rescaled and rotated by the local rescaling and local rotation. In the sense that conformal transformations locally look like rescalings and rotations because they reserve metric up to a factor. And the primary operators just feel this local rescaling, local rotation, and transform in some general way under them. The difference between primary operators and, say, derivatives of the primary operator is that in the transformation law for the primary operator, only the primary operator itself appears on the right-hand side and nothing else. If we were to put some derivatives of a primary on the left-hand side, so if we put the mu, let's say, here, then on the right-hand side, we would get extra terms in addition to the derivative itself. So the reason why we care about primary operators is that in unitary CFTs, it can be shown that all local operators are either primaries or descendants of the primaries. And by descendants here, I just mean the derivatives, the space-time derivatives of the primary. For example, in something like 3D easing, there is a spin field. There is a spin field sigma, which is a scalar primary with dimension delta equal to some number that we know to fairly high precision, and so it doesn't carry any spin index, but if you take something like T mu, the stress tensor, it transforms in the spin-2 trace of symmetric representation of Lorentz group and has also has some scalar dimension delta equals 3. So that's kind of the crash course in primary operators and conformal generators and conformal field theory and in higher dimensions. And before I move on with correlation functions, let me ask if there are any questions.
In the upper right formula, what is x prime there? How it is related to x?
So if, yeah, sorry. Thank you. The U is a fine conformal transformation which sends x prime. So it's just some function of x.
Okay. Okay.
Which is associated to U. And rho is the kind of the representation of the Lorentz group. Which R of x is the local rotation. So basically, I probably should have written this. You can write if you take dx prime dx and then you'll get that this is some function omega times an orthogonal matrix for conformal transformations. You can always factorize this matrix of derivatives, because it's conformal transformations locally or rotation and rescaling, so you can always factorize this derivative as an orthogonal matrix R times some scalar function omega. And so these two functions just go into this equation here.
Thank you.
Okay, so if there are no further questions, let's move on. So let's talk about correlation functions, conformal invariant correlation functions. So this is a standard story that I'm sure everybody has heard many times, but probably not necessarily in higher dimensions, in which case there are some differences from 2D. So as usual in conformal field theories, 2-point functions and 3-point functions are sort of fixed by conformal symmetry to some degree, and The reason for that is that conformal transformations, using conformal transformations, we can bring any pair of points to any other pair of points. For example, if we if you have points x1 and x2, we can always use translations, let's say, to bring x1 to 0 and then use rotations to make x2 point in some particular direction, and then use dilatations to fix the distance between x1 and x2. And the same is true for 3 points. Given any configuration of 3 points, we can use conformal transformations to turn it into any other configuration of 3 points. So for 2-point correlation functions and for 3-point correlation functions, it is then true that if we know these correlation functions in some configuration of points, x1, x2, or x1, x2, x3, then we can use conformal symmetry to compute it in any other configuration of points. So the functional form of this correlation functions of 2-point function and 3-point function is fixed, given that we know the value of them in one single configuration. Now, for 2-point function of scalar operators, let's say we don't have any indices a or b, and the value of the 2-point function in something like in some particular configuration of points, let's say when one point is at x equals 0 and the other point is at x equals, so say 1, 0, 0, 0. It's just some scalar, and we can say we can normalize the 2-point function so that the scalar is equal to 1, and then we know the 2-point function everywhere. For operators who spin, in general, we have some indices, and we have to specify a bunch of values in the standard configuration. And these values that we specify, they are constrained by the symmetries which preserve the standard configuration. And there are 2 particular types of symmetries which preserve 2 points. One looks kind of like this. It's kind of flows along these arrows. And what it does, it kind of zooms out on one point and zooms in on the other point. So when you apply the symmetry to this 2-point function, it kind of rescales one operator with scaling dimension delta 1 and the other operator with scaling dimension minus delta 2, where delta 1 and delta 2 are the scaling dimensions of O1 and O2. And the reason for that is that it zooms out on one and zooms in on the other. And for the 2-point function to remain invariant, delta 1 minus delta 2 has to be equal to 0. We choose the condition that the 2-point function can only be invariant if delta 1 is equal to delta 2. And similarly, there is another kind of transformation which rotates the 2 points also in opposite directions. So transformations kind of move everywhere. They have these 2 fixed points, and in the neighborhood of one fixed point, it rotates, say, clockwise. In the neighborhood of the other, it rotates counterclockwise. So because of the existence of such transformations, the invariant 2-point function can only exist if the indices a and b, if the index a can be paired kind of with a reflection of the index b. This requires that the Lorentz representations of these operators are related in the following way. So the Lorentz representation of O1 in Euclidean language, it should be dual. So dual here is the star to the reflected representation of R2. By reflection, I mean just kind of exchanging left and right chiralities. In the language of Lorentz group and language of Lorentzian signature, the statement is that the representation of Lorentz group Rho1 should be just complex conjugate to the representation of the operator 2, which is R2. And the complex conjugation Lorentzian signature I just denote here by dagger to distinguish it from Euclidean. But it's not super important. It's just saying that if you take operators O1 and O2 to be Hermitian conjugate to each other, then the 2-point function can be non-zero and uniquely fixed. And otherwise, if the quantum numbers are not as if you did this, then the 2-point function has to vanish. And in unitary theories, you can always choose a basis of local operators so that the two-point functions only are non-zero when the two operators are Hermitian conjugate to each other. And by changing normalization of these operators, you can always canonically normalize the two-point function so that there is no kind of dynamical freedom in two-point functions. For any pair of local operators after a suitable change of basis, we can write down exactly what their two-point function is. And that's kind of the same as in 2 dimensions. All two-point functions are fixed, and there is nothing particularly interesting which is introduced by existence of non-trivial spin. It's just more complicated formula, and that's all. For 3-point functions, again, the story is kind of similar, that we just need to specify 3-point function in one particular configuration, and then the 3-point function, all other configurations can be computed. But now the difference is that if we had, for example, scalars, or we were in 2 dimensions, this 3-point function in a particular configuration would be just a number, and we would say, okay, this number is some dynamical quantity that we need to know, but then given this one number, we can compute 3-point function in all other configurations. Now, again, if we fix points x1, x2, x3 to some standard configuration, we still have this indices A, B, C, and we have to specify more than just one number. Now, this is constrained by additional symmetries, which fix the 3 points, but in general, there can be several conformally invariant 3-point functions, which are linearly independent. So here I denote this conformally invariant 3-point structures by this T of x1, x2, x3. It carries this indices A, B, C, and the multiplicity is labeled by alpha. So in general, a conformally invariant 3-point function is some linear combination of this basis tensor structures with several 3-point couplings, lambda 1 to 3, also labeled by alpha. And this is some finite sum. In simplest cases, it just contains one element, but in general, it contains several elements. And the same is true for 4-point functions. Again, for 4-point functions, quite familiar, probably everyone is with the fact that 4-point functions are not uniquely fixed, and their cross ratios U and V, which are defined in the usual way. But the difference in higher dimensions from, say, 2 dimensions is that, again, there can be several 4-point tensor structures labeled by this large I, completely analogous to the 3-point structures. And we need to specify several functions, G of U and V, to specify the correlation function completely. If all operators are scalars, there is just one function, but more generally, there can be several, but always finitely many. And the situation kind of continues on for higher point functions. You just get more cross ratios, more tensor structures, and but the conception, nothing changes. Any questions about this part?
So what is this index labeling different tensor structures for 3-point function? So how to think about this?
Well, okay, you can think about it this way. You have functions of 3 points, right? So you can just write, say, I have a function, so this is equal to some f a, b, c of x1, x2, x3. Now I want to require that this f a, b, c is conformally invariant. So I can write some I can write this invariance conditions in some differential equation. So say dx1 plus dx2 plus dx3 acting on this should be 0. This gives the translational invariance. And you can write the same for all other generators. So you get a system of differential equations. And you can solve the system of differential equations and then get finitely many solutions. So this you'll get finite dimensional space of solutions. And this T with different values of alpha just give you a basis of this space of solutions.
So it isn't just a kind of a number, or it has some representation theoretic meaning?
Oh, so you can use representation theory to kind of classify the solutions, and then this index will have, can make it have some meaning. But for now, it's just that there is a finite dimensional space of conformally invariant three-point functions, and this labels just some basis elements in this space. So it will just go from 1 to some number, let's say. You can come up with some representation theory interpretation for this, and I'll probably come back to this later in the talk, but for now it's not important.
Thanks.
And same goes for this I. Now the space is infinite dimensional because the space of solution of conformal invariance equation are infinite dimensional over, say, complex numbers, but it's finite dimensional over the field of functions of U and V. This gives the basis of the space of solutions over this field of functions of U and V. Okay. So let's move on. Now, when we restrict to primary operators, you can use conformal symmetry to kind of repackage the operator product expansion. And so the operator product expansion for primary operators says that if you have two primaries, O1 and O2, and they have their spin indices A and B, sorted points X1 and X2, then we can write it as an infinite sum over all other primary operators. Well, in principle, we should write not just primary operators on the right-hand side, but primary and descendants. However, the conformal symmetry will fix the relationship between contributions of primaries and their descendants. And so usually the way we denote this is that the contribution of a primary is given by some function of x1, x2, x3, and d dx3, whereby a function of d dx3 we just mean a formal power series in d dx3. And if you expand this formal power series, you'll just get the sum of O, derivatives of O, and this kind of gives the contributions of all the descendants. And the form of these functions is fixed by conformal symmetry. And this function carries a bunch of indices. So there are indices A and B. There's index C, which contracts as the index of the primary. And then there is also, again, a multiplicity index, because when you try to solve the constraints of conformal invariance for this kind of functions, you find that there are several of them. And so there, in general, you have several OP coefficients that you need to specify. And you can always choose a basis of these functions such that these coefficients are precisely the same as those which appeared in three-point functions. To kind of match them, you can just use the OP inside of the three-point function, and you'll get an identity between what appears in the OP and what appears in the three-point function. And again, just to remind, the statement of the convergence of this OP is that if we take X3, where we insert these primary operators, we draw some sphere. We should be able to find some sphere around X3 so that X1 and X2 are the only operators inside of this sphere. And the physical reason for this is that we can interpret its correlation functions in radial quantization. So we have some Hilbert space on the sphere, and what is happening is that operators at X1 and X2, so O1 and O2, are just creating some state on the boundary of the sphere. And we are just expanding this state in terms of the states created by single primary operator insertions at X3. And this gives us all possible states by operator state correspondence. So we can, if we have a correlation function involving O1 and O2, we kind of insert the complete set of states inside and sum over these states, and the psi just run over orthonormal basis built out of the states created by OI and its derivatives. So that's just kind of the formulation of OP with all the indices and bells and whistles.
Sorry, question about radial quantization, because in two-dimensional conformal field theory, we map usual quantization to the radial one by exponentiation, and this is not allowed in three-dimensional conformal group.
Right. Yeah, you don't need this to. So the usual quantization is what's related by exponentiation is the quantization on the cylinder and quantization and the radial quantization on the plane. But what we do in higher dimensions is we start with quantization by kind of flat slices in flat space, and so this is a plane, and there is a conformal map which maps it to a sphere. So constant time, kind of t equals 0, gets mapped to r equals 1 by just some kind of inversion, because planes are always mapped to spheres by conformal maps. Does this make sense?
Yeah, but I'm trying to convince myself that things that we put infinity to some finite point on sphere is okay for quantization.
Right. So here, I think the important point is that when you draw this picture, you say this point at infinity. So what does it mean to have a point at infinity? So I'm trying to apply a finite conformal transformation, and you said this finite conformal transformation brings a point from infinity to some finite value. And we actually don't have a point at infinity in the first place, right? So to have a point at infinity, we need to work not in flat space, but on conformally compactified flat space. And so we take kind of RD and we add to it a point at infinity. And this becomes the conformal sphere. So when we do this, so when we say essentially in conformal field theory, what we say in Gooding signature is that we work on this conformal sphere. And what this really means is that we work in flat space, but we impose conformally invariant boundary conditions at infinity so that we can treat it as just an extra point there. In principle, we could imagine having not conformally invariant boundary conditions, and then you would not be able to perform this conformal map. And you would be right that there is a problem with this argument. So I think, for example, if you have a theory which can spontaneously break some symmetry, if you were to, including signatures, specifying a vacuum in which you work amongst specifying boundary conditions at infinity. So if you were to use a conformal vacuum with broken symmetry, spontaneously broken symmetry that would introduce a scale break conformal symmetry, and such boundary conditions at infinity would not allow you to do this transformation. So when I say this, I always assume that we work kind of in the conformally invariant vacuums, always conformally invariant boundary conditions at infinity.
Thank you.
Okay. All right, so getting to conformal blocks now that we discussed the OPE and the tensor structures and so on, we can just introduce the 4-point conformal blocks. So it's relatively straightforward. We just take a 4-point function of some generic operators, and we take OP between O1 and O2. So just using this formula from the previous slide, we replace it by sum over primary operators OI. We have this differential operator C here, our OP coefficients lambda, and we just sum over everything. Now we look at what we have here, and this is just a 3-point function. And we know that the 3-point functions of a constraint up to a finite number of coefficients. So we can use identity from the couple of slides back where we express this 3-point function in terms of OP coefficients for operators 3, 4, and I, and in terms of the standard conformal invariant tensor structures. And so we have that we can take our 4-point function and express it as an infinite sum over some intermediate operators OI, which is product of two OP coefficients, and times this combination of the differential operator C and the 3-point tensor structure. And both of these objects are fixed by conformal symmetry. So their combinations, of course, also fixed by conformal symmetry, and it has conformal transformation properties of a 4-point function. So we can expand it in 4-point tensor structures. We can write it as a linear combination of our basis 4-point tensor structures times some functions of U and V. And these functions of U and V are called the conformal blocks, the 4-point conformal blocks. And they have a bunch of indices. So they have this index I, which comes from the 4-point tensor structure. They have this indices alpha and beta, which come from the OPE operator and the 3-point tensor structure. So these indices pair up with the indices of the OPE coefficients, with the multiplicity indices of the OPE coefficients. And since this combination was completely fixed by conformal symmetry, this function actually does not depend on the specific operator OI. It only depends on its quantum numbers. It depends on the its scaling dimension delta I and then on its Lorentz representation rho I. And so this function of U and V is what we call the 4-point conformal block. And sometimes we draw this diagram that we took OPE of operators 1 and 2. There is intermediate operator I, and there is an OPE of 4 and 3. So, yeah. Are there any questions about these formulas? I mean, they're kind of heavy. There's a lot of indices. There's also some more beta that's missing. But they're not really conceptually anything tricky. It's just taking the OP and keeping track of all the multiplicities. Okay, so as I said, there is a bunch of information which goes into this conformal block. There is the 4-point tensor structure, the 3-point tensor structures. There is the quantum numbers of the exchange operator. It of course also implicitly depends on what are the operators in the 4-point function. Sometimes we call them external operators, so it depends on the dimensions delta I and Lorentz representations rho I of this 4-point function that you started with, but it doesn't depend on actual operator. It only depends on their quantum numbers. So in principle, if you specify some particular choice, some numbers for delta I, some particular representations for rho I, some particular number for delta, some representation for rho, then you choose some indices alpha and beta and I, which are appropriate for all these operators. Then you specify some values for U and V. Then you can finally plug this all into this conformal block and get a number. So that's kind of a beefed up version of SL2C conformal block from 2D conformal field theorist, which has a lot of more indices, but conceptually it's the same thing. So the simplest example of these conformal blocks come from the correlation functions of scalar operators, in which case we don't worry about this alpha, beta, and I, because they can just take only one value. There is a single 3-point tensor structure, there is a single 4-point tensor structure, so we don't usually specify them. Now the exchanged operator can have any scaling dimension, but the Lorentz representation for scalars is constrained to be traceless symmetric tensors. So only traceless symmetric tensors can be exchanged in 4-point functions of scalars. They have these Young diagrams, which have one row and the number of traceless symmetric indices we denote by some spin j. And so we get this conformal blocks, which usually denoted by G delta J of U and V for the scalar 4-point functions. However, it's really the simplest of the simplest conformal blocks that you can think about, because it really quickly gets out of hand as you start increasing the spin of the operators in 4-point function. For example, if you take 4 spin 2 operators, so like stress tensors, in 3 dimensions, then the number of 4-point tensor structures is 625, and each alpha and beta can take 25 different values. And in addition to that, the types of operators that can be exchanged also, the number of types of operators that can be exchanged also grows. So for example, in 3D, of course, all representations are just trace symmetric tensors, so the question is not interesting, but if you go to d equals 4, then the exchanged operators in 4-point function of spin 2 operators are 2-row Young diagrams with any lengths of the first row, and the second row can be of lengths 0, 1, 2, 3, 4. So there are 5 different families of exchanged operators for the spin 2 operators in 4D, and the number of i's and alphas is even more than in these examples. So
Can
it's
it again in this example, is the first example. So you said that I, alpha, and beta are with this unique choice. So delta in our case, rho in our case is correspond to trivial representation. We have delta, and where's J? It's not I, not delta, not rho, not alpha, not beta. Where is J? Red in.
So J is a row for the exchanged operator. So row for the exchanged operator is traceless symmetric.
But
So,
it doesn't appear in your sum. Can you write down the formula from previous slide for this particular case?
so in this
this
formula,
lower one.
yes. So this formula here the sum is over I, which label different primary operators OI. So here I wrote delta I and rho I here. So for if these 4 operators are scalars, then what will happen is that the sum over I will only go over such I that rho I are traceless symmetric. It will only go over operators OI for which rho I is traceless symmetric. And the reason for that is that you cannot write conformally invariant 3-point structures for 2 scalars and not traceless symmetric representation.
So there will be some unique T, A, B, C, D, I big, yeah? But there will be still sum over I small.
Yes. Yes, exactly. So the sum over I small always remains because you're just summing over all kind of primary operators in your theory. But in case when O1, O2, O3, and O4 are scalars, the sum over alpha beta goes away, and the sum over I goes away, and you're just left with a single function, so without these parameters.
Thank
But
you.
you still go over different rho i's, and it's just that in the case of trace symmetric representations, rho I is parameterized by one number, which is spin, and I denote it by J. If you take, say, external operators to be 4 spin 2 operators, then this rho i's will go over various Young diagrams. There's 2 rows in 4D. In higher D, it's even more rows, up to 4-row Young diagrams. And the first row is not constrained, so it can be any lengths, but the subleading rows will have some selection rules on them, but there will be like many of them, not just traceless symmetry. It's probably a bit confusing because here I use delta I and rho I, which is kind of the same in the previous slide, but what I really meant here is well, I meant delta 1, delta 2, delta 3, delta 4, just for the external guys, which appeared in the 4-point function. Okay. So I'll first focus on the scalar blocks and discuss how they can be computed, and then move on to discuss what can we do with this monstrous conformal blocks with spin.
Can you comment again about previous? So we have some list of indices. Can I somehow graphically think that alphas correspond to alpha and beta correspond to vertices? I is to intermediate Rho, I small, I capital to what?
Okay, I can try to draw a picture for this, okay? Let's change this a little bit. So sometimes people write like this. There's going to be alpha here. There's going to be external exchange operator, going to be OI. And there's going to be beta labeling this vertex. And this exchange is kind of a sum over I, some standard structures. 1, 2, 3, 4 times functions of UV. So essentially what we are doing, well, this summing over all I, essentially what we are doing is we're taking two 3-point functions and gluing them together to get a conformal block. We're summing over different conformal blocks for all the operators. Then we're expanding this sum into basis of 4-point structures, which are labeled by I. Does it make more sense now? Should I try something else?
Actually, I still don't understand what is the meaning of I capital. On the left side, I see we have structure for 3-point vertices and we have intermediate fields. What is I capital?
So yes, okay. So here what I'm doing, I'm taking this 4-point function, and then I'm starting to use OP and this 3-point function. This process introduces for me this alpha and beta, which are just the 3-point vertices, as you say. So far, no I has entered, right? But if I look at the subject has the same transformation properties as this 4-point function. And for 4-point functions, we discussed that 4-point functions can be written as sum over I, and then there's standard tensor structures, A, B, C, D, I, x1, x2, x3, x4, times functions of U and V. That's the statement about conformal invariance for a 4-point function. For example, in scalar case, I can only take one value for scalars. There's just one index. And T is T1. And there is no indices here because it's just scalars. They don't have indices. Of x1, x4 is something like 1 over x12 delta 1 plus delta 2, x34 delta 3 plus delta 4, and then a couple of other factors of the same kind. So this thing just has the transformation properties the same as the 4-point function of scalars, and then we just multiply it by a function of the conformal invariant function of the conformal invariant cross ratios. The statement is just for scalars, there is just one such thing that we can write. For operators as spin, there can be several, and we just need an index for them.
Maybe I somehow convinced myself that everything is okay. Is it true in general then if alpha and beta are just one element, there's no non-trivial 3-valent vertices, then there is no non-trivial 4-valent vertice?
Yes.
If you have such for field, or maybe there's no examples.
So the question that you have to ask is that there are kind of different families of operators that can appear. And what you need to do is you need to take number of alphas times number of betas. And these numbers, they depend on which family of operators you put in. You need to sum over all families. And that sum of number of alphas, number of betas over all families is going to be the number of i's. So if there is only one family, and for this family there is no non-trivial multiplicity, so there is only one alpha and only one beta, there will only be one I. And by families, I mean here basically like traceless symmetric operators are one family. Operators with, say, any number of boxes in first row, but one box in second row is another family. In 4-point functions of scalars, only traceless symmetric operators appear, so there is just one family, and there is no multiplicity for alpha or beta for this single family, and so there is just one I. If you have several families, then even if alpha and beta can take only one value, there will still be several 4-point structures.
Okay, thank you.
You can think about this as a sort of Fourier transform. So here you have functions of two variables, u and v. So in the left-hand side, you kind of also have functions of two variables because you have this OP coefficients, well, squared, there are two of them, but this product of OP coefficients depends sort of on scaling dimension and spin of the exchanged operator, where by spin I mean length of first row of Young diagram. And but since there can be several 3-point functions and several types of operators that can be exchanged, the number of functions that you need to, of two variables that you need to specify on the left-hand side is what I said, the number of alphas times the number of betas summed over all families of operators. And this number of functions of two variables that you have on the left-hand side should match the number of functions of two variables that you have on the right-hand side. And you can check in examples, it explicitly matches, and you can prove that this is true in general. Okay. So let's discuss scalar blocks. And scalar blocks, as I said, I just know they don't have any indices, so they're functions of delta and j. And it's the cross ratios u and v are nice because they're easy to define in terms of x1, x2, x3, and x4, but they're not convenient for discussing the properties of these functions. So the better set of variables is z and z bar, which are related to u and v in this way. And physically, the meaning of z and z bar is that if you take 4-point function and you put the 4 points at positions, so you put operator 1 in some plane at coordinates 0, 0, you put operator 3 at 1, 0, you put operator 4 at infinity, and you put operator 2 at some position xy, then z is x plus y, x plus iy, and z bar is x minus iy. So since in Euclidean signature x and y are real, z and z bar become complex conjugate. But in general, as far as studying this function goes, or if you, for example, recreate Lorentzian signature, z and z bar are two independent complex coordinates. So z and z bar don't necessarily have to be complex conjugate to each other.
Sorry, are these all 4 points in the same two-plane?
Yes.
Why?
I'm just explaining the meaning of z and z bar. So
no, well, is it general case or for this particular choice?
So for 4 points, if you have 4 points, you can only map 4 points with given values of cross ratios to any other 4 points with the same values of cross ratios. What I'm saying is that you have 4 points with cross ratios u and v, and you can compute z and z bar according to these formulas. Then what you can do is you can take your 4 points and apply conformal transformation, which will map them to this configuration when they all live in in two plane, and the only point which is kind of at random position is point number 2. It's position x and y are related to z and z bar in this way.
Thank you.
So the functions g delta j or z in z bar, they are functions of two complex variables. And if you look at these functions, let's say look at them as a function of z, the function of z, then the most interesting, well, first of all, you find that they have a cut along negative real axis and a cut along positive real axis starting at 1. And the most interesting region in the complex plane is away from this cuts. You can, of course, ask what happens when you go under the cut, but it's not as interesting as the region without going under the cuts, because this is the region in which the conformal block expansion, so this expansion in this slide, so the sum over I, this is the region where the sum converges. And numerical bootstrap works when z and z bar are both near 1/2, and other important points in this plane are 0 and 1. So when the cross ratios approach 0, it's the same as 1 approaching 2, or 2 approaching 1. So it's the OPE limit for 1, 2. Or when z approaches 1, that's the OPE limit for, when z and z bar both approach 1, that's the OPE limit for 2 goes to 3, or equivalently 1 goes to 4. Similarly, you can also take to infinity, and then to infinity is going to be 2 approaching 4. And the picture is the same in z and z bar. So most of you are interested in this function for z and z bar kind of on the first sheet of complex plane without going under the cuts. And for numerical bootstrap, we are mostly interested in kind of computing the function in this area, but for some more analytic approaches, lots of other limits are interesting. Let's say we can take just z going to 0 and z bar not going to 0. This is slight quantity, and so on. And sometimes it's also interesting, say for edge physics, it's interesting to get one of the cross ratios to go under the cut. But I'm not going to go into details for that. I'll just discuss this simple region here. Now, how much time do I have? I thought something like 1.5 hours is okay.
How much time do you need?
I think half an hour should be okay.
Okay, go on.
I don't want to force anybody to stay longer than they want.
Everyone is free to leave if needed. So
Okay. Right. So I'll discuss briefly a couple of approaches for computing scalar blocks, and which are listed here, and then I'll move on to the spinning blocks. The first approach is to just compute them by definition. And as I said, we can think about conformal blocks. So previously, we can think about conformal blocks as taking our 4-point function for 1, or 2, or 3, or 4, and sticking in a complete sum over states in the middle, and identifying the states with states created by primary operators. So the basis of states created by primary operator OI is given by radial quantization by OI itself. There's a spin index that I'm missing. It's a derivative for equivalently p mu acting on the primary state, 2p's acting on the primary state, and so on. So this kind of structure of states is sometimes called generalized Fermat margin. Now the problem with these states is that in general they're not orthonormal. The states with different numbers of p's are orthogonal to each other, but there is no simple orthogonality property, for example, for states with 2p's. And to compute kind of the resolution of identity in terms of the states, we need to compute the matrix Q of inner products between them. So we take the state created by O in a bunch of P's. We take its conjugate state, where the function conjugation replaces P's by K's and sends O from 0 to infinity. And we get some matrix, which we can compute by using commutation relations. So as usual, we move K to the right using commutation relations, and then eventually K will hit O at 0 and give 0, and this way we can get rid of all the K's and use the scaling dimension of O and the Lorentz transformation properties of O to compute this value. And once we know this matrix, then we can compute its inverse, and the sum over states here becomes the sum over all the indices with this inverse matrix inserted. And we can just then compute it because these things are 3-point functions. Acting with conformal generators is just taking some derivatives of these 3-point functions. So plugging in some conformal invariant 3-point structures for this functions, we can take their derivatives and compute this value, compute this value. We have just computed this value, and this way we get some expansion for the conformal block. And in terms of the Z and Z bar variables that we discussed earlier, it's an expansion near this point. It's expansion in terms of small, which is valid for small Z and Z bar. And I'm not going to focus on this anymore longer because it's a really, really inefficient way of computing things. You can do this. It's good for kind of theoretical understanding what this conformal block is, but it's completely useless for any practical calculation. You can compute maybe the first few terms, but then it quickly gets too hard to do in Mathematica. So unless there are any questions about this formal expression, I'll just move on to more practical ways. Okay. Now the probably first practical way of computing conformal blocks, like first really powerful way of computing conformal blocks is based on so-called Casimir differential equation, which was introduced by Dolan and Osborne. And it basically is based on the observation that the conformal algebra is SOD, 2, and it's some semi-simple algebra, and in general, and such algebras have Casimir elements. So they have elements which generate the center of the universal enveloping algebra. For example, you have the quadratic Casimir, which in terms of explicit conformal generators is given by this expression, and its claim to fame is that it commutes with all the conformal generators. It's some particular polynomial, quadratic polynomial conformal generators, and it commutes with P, it commutes with K, it commutes with M, and it commutes with D. For example, it's obvious that it commutes with D because all terms here have scaling dimension 0. D has scaling dimension 0, M has scaling dimension 0, and P and K have scaling dimensions +1 and -1, which cancel in this product. It's also obvious that it commutes with M because M is Lorentz generator and all the indices here are contracted in invariant ways. And the only trivial fact is that it commutes with K, so you can just use the commutation relations and check that this is true. Now, and useful rewriting of this formula is by using commutation relation between P and K to, in this term, to move K to the right. So it becomes 2 copies of this term, so we get minus PK, but it introduces some combination of dilatation and just changes D squared to D times D minus D minus small d, where small d is the space-time dimension. And you can also observe that this part is just this, the Casimir of the Lorentz group, a quadratic Casimir of the Lorentz group. And using this formula, we can compute, for example, the action of this quadratic Casimir on the primary operators. When we act on this Casimir on the primary operator, this term drops out because we have k to the right, so it annihilates out 0. Then we have this term just acting obviously by delta times delta minus d, and this term just acts by the Casimir eigenvalue of the Lorentz group. For example, for trace of symmetric tensor, it's given by j times j plus d minus 2. So for example, in 3D, this is j times j plus 1. And this is the familiar formula for the Casimir for j squared, the eigenvalue of j squared in 3 dimensions. Now, the usefulness of this generator with this Casimir element comes from the fact that it commutes with all conformal generators, and since the conformal representation generated by primary operator is irreducible, Bashir's family has to act by the same eigenvalue on all descendants. So if we insert some bunch of p's here, it will still be the same formula with the same eigenvalue. It's just going to be less obvious than for the primary, because now we won't be able to discard this term, but this term will precisely make sure that everything is consistent and C2 acts by an eigenvalue on all descendants of O as well. And that's the key property that we're going to use. Are there any questions about just this basic facts about Casimir? Okay, so now we can just go back to our expression for conformal block from the first method, from computing kind of by definition, and modify it a little bit by sticking in a Casimir in one of the 3-point functions. Now, since we have this quadratic Casimir in this 3-point function, we have 2 ways of computing its action. One way we can compute its action on the left on the primary OI. And this way, as we just discussed, is going to act by an eigenvalue. Currently, we could have inserted it here, but it doesn't matter. But on the other hand, we can compute its action on the right. And acting on the right, it acts on 2 operators, on O1 and O2. They're not, so it's not going to be an eigenvalue. However, C2 from this definition is just a combination of conformal generators. Conformal generators act by differential operators on O1 and O2. So when we act with C2 on the right, we just get some differential operator acting on X1 and X2. And if you unwrap what this differential operator is, then you get some differential equation for the conformal block for G of EV. There is some differential operator, and it just which comes from here, and it should be the same as acting with C2 to the left. It just gives us Casimir eigenvalue that we computed on the previous slide times the function. And in the ZZ bar coordinates that we discussed previously, introducing some A and B for the differences of scale and dimensions of the scalars, you get some explicit expression for this differential operator. And you see that it's some relatively involved but very explicit differential operator. And the important feature is that the first line of this equation is kind of factorized between Z and Z bar. You also have expressions in Z plus expressions in Z bar, Z, Z bar, Z, Z bar. However, the last term in the second line kind of mixes Z and Z bar. You have this Z times Z bar divided by Z minus Z bar. And it comes with a factor of D minus 2. So if you set D equals 2, then conformal algebra is SO2, 2, which factorizes into 2 pieces, holomorphic and anti-holomorphic, and we can solve for Z and Z bar independently because this term disappears, and the terms in the first line all factorize between Z and Z bar. However, in higher dimensions than D equals 3, 4, and so on, we cannot drop this term, and this is some non-trivial differential equation in both Z and Z bar. Now, this differential equation in Z and Z bar, it's a single equation for a function of two variables. And so to have a unique solution, you need to add the asymptotic at Z equals. You need to add some boundary conditions, and what people use in practice is the asymptotic at Z and Z bar goes to 0, which corresponds to the OPE limit as we discussed between operators O1 and O2, and we can just compute the leading term by computing the first contribution of level 0 descendants to this formula. So the asymptotic we know, that's easy to compute. And using this asymptotic and this equation, we can then try to, given this asymptotic, this equation has a unique solution, so we can try to use it to compute conformal blocks.
Sorry, probably I missed. What is the definition of a vector containing two operators from in radio quantization?
Sorry, can you repeat the question again?
What is the definition of the vector containing two operators in radio quantization?
Yes, sorry, it's a bit of shorthand notation. It's simply O1 of x1, O2 of x2. Actually, in the vacuum, it's nothing fancy. Just the operators are there inserted in the vacuum. Does this answer the question?
Yeah, thank you.
Sorry, can you also a little bit repeat? So your coefficient B depends on delta 3 and delta 4, right?
Yeah.
And so you say that it appears from computation of an eigenvalue.
No, B doesn't appear from computation of the eigenvalue. B is just, it enters in this differential operator D. So
yes.
B appears here. This is just differential operator D, and D appears from acting with C2 on the right onto O1 and O2.
Yeah,
so
but
C2,
how delta 3 and delta 4 shows up?
all right, so very good. So this differential operator, indeed, it's going to be only in x1 and x2. However, this differential operator is going to be acting on G of EV times the 4-point tensor structure, times some product of x1, x2, x3, and x4 raised to various powers. And that tensor structure depends on delta 1, delta 2, delta 3, and delta 4.
So it arises when you retranslate it from correlation function to this G, yeah?
Yeah, it arises when you go from x1, x2, x3, x4 to UNV.
From these prefactors which you have.
Yeah, exactly.
Thank you.
And it's really important to actually translate there, because in x1, x2, it's terrible operator, and there is a nice choice of prefactor which gives this equation and this differential operator, and other choices give much nicer expressions somehow. All right, so yeah, so there's a few properties of this differential equation. So in D equals 2, as I said, it factorizes. In general, turns out that this equation can be solved exactly in terms of 2 of 1 hypergeometric functions in any even number of dimensions. This was found by Dillon and Osborne as well. For example, in D equals 4, the solution is taking this form. It takes this form. There is some prefactor which is not kind of factorized between Z and Z bar, so Z times Z bar over Z minus Z bar. But then it multiplies some factorized function, which is one function of Z times another function of Z bar. And this K beta is just the hypergeometric function of its argument. So you can just take this, plug into the equation, check that it's satisfied, check that the OP limit is satisfied, and this is proves that this is the conformal block for scalars in 4D. Another nice property of this equation is that you can find some differential operators in Z and Z bar which have nice commutational relations with D, with the operator D which appears in the equation. So with this guy, and it has nice commutation properties. You can prove identities that if you take this nice differential operators, you act with them on conformal blocks, then they will change. They will do something nice to this conformal block. For example, Dole-Nosbury derived differential operators, which can change A and B of the conformal block by ±1/2. They can change the exchange dimension or spin by ±1, or they can even change the space-time dimension by ±2. This is kind of the various identities that exist for hypergeometric functions. Like if you differentiate hypergeometric function with respect to x, you get another hypergeometric function with different arguments, and this converts into changes in A and B, or changes in this beta, which transforms into changes in delta and J. And there are some very nice combinations with derivatives in Zinzibar, which make everything work so that you're just changing A and B, just changing A, or just changing B, or just changing delta, or just changing L, and so on. So you can look at Dole-Nosbury's papers for this. That's been used some time ago to actually compute the scale. To compute the conformal blocks, for example, people would compute conformal block with spin equals 0, and then use this relations to compute conformal blocks with other spins. Another nice property is that, as Nishlai Walter Shammer has found, is that this differential equation is actually equivalent to some interesting system from integrability theory. I know very little about this, but if you read their paper, they'll tell you that it's BC2 root system, hyperbolic Fourier-Sutherland model. And there's a lot of kind of mathematical theory about this equation, about its solutions, and they explain how all this translates into the scalar conformal blocks. And they, for example, they can rederive these formulas by Dole-Nosbury in this kind of high-level language, and so on. And you can also use this differential equation when you say d equals 3. We don't know how to solve it explicitly, but even d equals 3, we can use it to produce various series expansions for conformal blocks and many other uses. Okay, so I'm just going to move on to briefly mention another approach, which is that there exist some integral formulas for conformal blocks, and that's usually called the Shadow Formalism. And the basic idea is relatively simple. Let's just consider this integral. You take a 3-point function of two scalars and an operator, trace symmetric operator O. So it has some trace symmetric indices mu1, mu_j. And this doesn't have to be a physical 3-point function. It just can be this tensor structure. And this operator has scaling dimension delta and spin j. Then we take another 3-point tensor structure, which is now for an operator of spin j, but with scaling dimension d minus delta. And operators, some other scalar operators, phi3 and phi4. And we put these two operators, O and O tiled, at the same point x, and we can track their indices. So now, since we've done this, at point x, we have something which transforms like a scalar, because we have contracted all indices, and has the dimension, scaling dimension d, because delta plus d minus delta is equal to d. And this transformation property precisely cancels the transformation property of the measure with the integration measure under conformal transformations. So
excuse me, I missed. So these O and O tilde originally, what do you say about them? So these are primaries, or?
These are primaries, so the all operators that I'm writing are primaries. But I'm just saying that they don't have to be, I mean, likely you won't have a pair of operators in your theory which satisfy this. Here I'm just talking about kinematics. I'm saying, let's take a 3-point function. Let's imagine. Let's
so you assume that your theory contains such operators, or?
No, I don't. I'm just saying, let's just take the formal expression. So like what I'm really saying, let's put here a 3-point tensor structure, and I can choose any quantum numbers for the tensor structure. And I'll just choose delta and j. And here I'll put another tensor structure, which will have quantum numbers d minus delta. But if I I know that I introduced a different notation for the 3-point tensor structures, but if I have written this 3-point tensor structures, in this way, it would be very hard to understand what I really want to do. So let's just imagine that we have by these expressions, I just mean explicit formulas like 1 over x1, 2 to some powers, x2, 3 to some powers, and so on. They don't have to be physical correlation functions. I just want any function which transforms in this way, in this conformal environment. I have probably really overcomplicated this. I just want to take conformally invariant 3-point function, which is just some explicit expression, another conformally invariant 3-point function, and just combine them in this way. And I'm just using this notation as if they were physical 3-point functions to explain how I'm combining them. So I can write this in terms of this tensor structures T of x1, x2, x3 that I introduced. It just wouldn't be very intuitive notation. So perhaps I should have done that. I hope it's clear. I can always just write these explicit expressions. I know that doesn't make sense. I feel like I've said too many words. But it's not physical operators. It's just some explicit functions.
Okay, maybe I have to wait while you make any further statement.
Okay. I take standard conformally invariant 3-point tensor structure, which transforms like this, and another standard conformally invariant 3-point structure, which transforms like this. And I combine them by contracting the indices of the traceless symmetric operator and putting them in the same point. And then I get some explicit expression which depends on 5 points, x1, x2, x3, x4, and x. And I integrate this expression over the point x. And I'm saying that this integral is conformally invariant. The reason it's conformally invariant is because at point x, I have something which transforms as a scalar of dimension d. And scalars of dimension d transform by just rescaling by some, by Jacobian, they just transform by rescaling by Jacobian raised to such power such that it precisely cancels the transformation of the measure, of the integration measure. And so this integral on the whole is conformally invariant. And so it produces something which is a conformally invariant 4-point function now, because it depends, after you've done integration, it depends only on the x1, x2, x3, and x4. And you can also check that this conformally invariant 4-point function will satisfy the Casimir equation, because the Casimir equation amounts to acting with conformal generators on x1 and x2. But since this tensor structure is conformally invariant, we can trade this action for conformal generators acting in this O. But since conformal Casimir acting in a single primary operator acts by an eigenvalue, we therefore prove that this integral gives something which is an eigenfunction of the conformal Casimir differential operator that we discussed previously. So it's almost like a conformal block. The problem is that while it satisfies the Casimir equation, it has wrong asymptotics. So if you take x1 to x2, you cannot actually easily compute its asymptotics, because in your integration region, when you integrate over x, there are situations when x approaches x1 and x2. And it's not clear how to verify the asymptotic of this integral because of this. And when x approaches x1 and x2, this 3-point tensor structure becomes singular. So that's what introduces the problem. And indeed, you can work this out and you find that this integral gives a linear combination of conformal block for delta j and a conformal block for t minus delta and j, instead of just the conformal block that I want. And but this is not too bad. There are some tricks which you can do so that giving this expression, if you have sufficient suitable form for this expression, you can actually figure a way to project out this bad term, or you can modify the integration region slightly. You can do this integral invariance and signature in various ways to make it produce this form. And I just wanted to mention this kind of approach because it doesn't really give you a practical way of computing numbers, but it gives a simple expression for something which is close enough to a conformal block, and it allows you to study some formal properties of it. You can prove things about conformal blocks by studying this kind of expressions, because they're very simple. They don't involve any infinite sums or inversion of some matrices or anything. Are there any questions? Okay, so I'm not going to discuss this integral further. I just wanted to mention that there are such representations. So feels like I'm not going to be able to discuss spinning operators, but if I still have some time, I want to discuss this homological-like recursion relations, because that's really the way we are computing conformal blocks today. Do I have time to continue?
I have a suggestion. It seems that the most interesting part is coming. So why not to consider the possibility to give another talk, maybe in a week or two, just to have more time and talk about homological.
That's
because it's not likely that you can finish in any reasonable time.
Yeah, that's true. I realized that I mean, I was told that I should give some review, and I feel like I've.
No, it's okay. But I
got too entertained by giving a review.
So just it's part one. Then whenever you find it's convenient, maybe in a week or two, you give the second part of the talk.
Yeah, that will work for me. That's fine. Maybe
we prepare some more concrete question about what we want to hear. Okay, so.
Yeah, that would also be great.
What other things about any suggestions, Andrei?
Well, I would certainly prefer to not to rush up now and maybe to listen once again, and maybe we can ask Pasha, yeah, to discuss preliminary the plan for next time.
No, I think there's rushing in this part. It would be just unproductive. I'm more interested to hear more details.
Okay. So
question to Petr. So you have time when next time in a week? When?
Yes, I'm locked in an apartment, and between apartment and office, I don't. I have all the time in the world.
Okay.
Andrei, do we have something scheduled for the next week? No.
Who is the chairman of the seminar? I don't have this time.
Okay, so if it's okay, let's have a part two in a week.
Okay. I'm pretty sure I can do in a week, but I'll just like confirm and write to Pasha maybe on someone.
So
thank you.
Any questions?
Yes, so I want to ask about these differential equations. Is it correct that there is one more Casimir because it's SO5, and we can get something from that Casimir as well?
Yes, that's true. So in general, so in the lowest kind of interesting case, in 3 dimensions, you indeed have 2 Casimirs, the quadratic and quartic Casimir, but in higher dimensions, you have even more Casimirs. You can have cubic and 4D and so on. And they are, they're not strictly necessary to say compute the conformal block because already the quadratic Casimir and the asymptotic of the and the asymptotic at small z bar completely fixes the solution. But they're useful. For example, one thing that you can do is that by combining quadratic and quartic Casimir, you can write a differential equation for function g delta j of z comma z. So you restrict to say z equals z bar, and you get function of one variable. Sorry, z comma z. So you restrict to z equals z bar, and you now have a function of one variable. And you cannot, since Casimir equations has independent derivatives, and the quadratic Casimir equation has independent derivatives in z and z bar, you cannot say anything about this function directly from that equation. But by combining this quartic Casimir, you can get rid of the derivatives which are transversed to z equals z bar line, and just get an equation for this thing. And there is an interesting fact actually about this, is that in 3 dimensions, we don't know the expression for g delta j of z bar, but we know an expression for g delta j of z comma z. So there is an explicit expression due to Ryczkoff and Ivernay for this kind of, it's called on the diagonal because z equals z bar. So for the conformal blocks on the diagonal in 3 dimensions, there is an explicit expression for scalars, and it is obtained by precisely using this quartic Casimir.
And what is this expression? Maybe just approximately.
So okay, so you need to introduce a new variable r. It's z over 1 plus square root of 1 minus z squared. So in terms of this variable, come on, sorry. In terms of this variable, the expression is something like 1 over 1 minus r squared, and then there is, I think, f(32). Then there is a bunch of numbers, and then it's r squared here. But this is for all equal external dimensions. So this parameters a and b are equal to 0. Delta 1 equals delta 2, and delta 3 equals delta 4. I'm not sure if it can be generalized to non-equal dimensions. I don't know. The expression that's in the literature is for the equal ones.
Where from this variable comes, this r?
It's the variable which maps. So in terms of r, so this region of complex plane, this region of complex plane minus 2 cuts, it's mapped to the unit disk of r. It's usually called rho. So the unit disk of rho is this blue region. And it's important, like the easiest way to see why you might care about this variable is that if you take the limit delta goes to infinity, then the conformal block has asymptotics r to the power delta. There's this formula, there's also r to the power delta here.
So is it something like a elliptic parameterization of 2D conformal blocks, or it's something different? Maybe in the philosophical sense.
You mean this Q variable?
Yes.
It's, I guess it's philosophically similar, but it's not related to Q. It's kind of, it uniformizes the C variable, but not kind of not completely. There is no similar story with like torus and stuff. This Q.
Thank you.
More questions? Okay, we'll wait for the next week to ask them. Thank you, Petr.
Right, thank you.
Спасибо.
Thank you.
Спасибо.